We'll again focus on strictly proper rational functions, and we will study what happens when we have multiple real poles. For example, this function has a double real pole at -1 and a single real pole at +3. Again, we will use a partial fractions expansion. Suppose that the denominator of f has a pole z with multiplicity kappa. That is, it can be written like that. Then the partial fractions expansion associated with this root is not merely a over s minus z, but it is a1 over s minus z plus a2 over s minus z squared up to a kappa over s minus z to the power kappa. We know how to take the inverse Laplace transform of the first term. Generally, the inverse Laplace transform of 1 over s minus z to some power nu is given by this formula, which is easy to verify. You can try this as an exercise. As an example, let us determine the inverse Laplace transform of this function, which is clearly a function with a double pole at -1 and a single pole at +3. In other words, f has 3 poles, s1 is equal to -1, s2 equals to -1 again, and s3 is equal to 3. Firstly, we need to expand f as a sum of partial fractions as follows. The 3 fractions involve the terms s minus 3, s plus 1, and s plus 1 squared. We now multiply both sides of this equation by s plus 1 squared times s minus 3. Like that. We rearrange the terms on the right hand side, we compare the corresponding coefficients, we solve a linear system of equations, and obtain the values of a, b1 and b2. We plug these values in the partial fractions expansion of f, and we can write f as follows. We have written f in a partial fractions expansion. In order to apply the inverse Laplace transform on the last term, we use the following identity, and we arrive at the inverse Laplace transform of f. You can try to determine the inverse Laplace transform of the following function by yourselves. The only difference now is that we have s plus 1 cube. Some qualitative remarks. We know that zero poles produce constant functions. Negative poles give decreasing exponentials and positive poles produce increasing exponentials. Now, double zero poles produce f of t is equal to t, and triple zero poles produce a quadratic function, and quadruple zero poles give a cubic function of time. Moreover, double negative real poles give a function of the form t times exponential of minus at, which converges to 0. Triple negative real poles give a function that involves t squared times exponential of minus at, which again converges to 0. And double and triple positive poles produce time domain functions which diverge. We can conclude that if all poles of f are negative real numbers, be they single or multiple, then the corresponding inverse Laplace transform will be a time domain function that converges to 0. If f has at least one positive real pole, then the inverse Laplace transform will diverge.